And now we have the final speaker. Stefano is going to be talking about cooling people with air movement. Thank you. I'll pass it straight on.
Thank you very much. We are facing a cooling crunch, meaning that right now we are using a lot of energy for cooling, according to the International Energy Agency, roughly equivalent to the total amount of energy that Africa is using in 2.5 years. We use it globally only for cooling. This amount of energy is going to increase, and it's not going to increase mainly for climate change. There are two main drivers to this phenomenon. One is population shift. Most of the population growth is happening in the tropic. Right now, around 40% of the global population live there. In the future, it will be around 60% of the world population. I'm thinking places like Indonesia, India, Nigeria, Brazil, and so on. The other important aspect is the economic growth, and a particular type of economic growth. If we divide the world in four groups, low-income country, middle-low, middle-high, and high-income country, the middle-low, we have something between 2.5 to 3 billion people living there. They are moving up, and usually that is the moment where they can start to be able to afford air conditioning. And the International Energy Agency is aware of this problem and have two main strategies. One is to develop better air conditioning and selling minimum rating for this type of system. The other one is developing and trying to spread labeling system that tell, if you can afford, try to buy a better air conditioning. It also says something about building and the ability to improve this building, but one aspect is missing completely. It almost never mentions fan as a solution to keep people in comfort. And that is the topic of today's presentation. Before going there, I want to just give two pieces of information. This one is based on the CB, Occupant Satisfaction Database. We have been using it for almost 25 years now, and we went to roughly 1,000 buildings with almost 100,000 people. And what we found is that 40% of the people are dissatisfied with the thermal environment, and only 40% are satisfied. In these days, we have been talking a lot about 80%, 90% acceptability, but when we go into real building, around 3% of the building in our database meet thermal comfort standard. There is a lot of work to do. Another interesting point is a study that we have done by looking at our database and completely independently by looking at tweets that people can send from their office. And we look at the difference between male and female in their feedback. And we found in general that female are much more dissatisfied. And you can see over here, both in summer and in winter, the problem is that they tend to feel too cold. And if you look in the summer, 75% of females feel too cold, while only 24% feel too cold of the male. So we are overcooling the building, and we have an unfair situation in front of us. So let's talk about fan. Fan are very affordable. If you think about it, it's basically a motor and some molded plastic. It's way cheaper than having two coils, a refrigerant, a compressor, and some control related to it. We can make fans that are very, very cheap. Here you have a range around hundreds, but easily you can now find around $5 to $10. Fan use very little energy, 1/10, 1/100 of an air conditioning. There is now high-cost fan, a ceiling fan that can move a lot of air and use between 5 to 10 watts. You can buy desk fan that use very little energy. Moreover, even that they give some kind of personal control, it may also be possible they are more comfortable. So they are more affordable, they are more sustainable, they are more comfortable. Why are we not seeing them everywhere? And so we've been thinking about this for quite a long time, and this is the collective work of many colleagues. So today I'm not giving a presentation about a specific project, a little bit more of an overview of this issue. There are technical challenges. When we start to look at this problem, the last paper published about fan were probably from the 60s. Yes, here and there was a paper, and so if you're young and if you want to find a field of research where there is tons to do, that's exactly a field where you can give an important contribution because very little is out there. There are regulatory limitations, and there is also cultural aspect. Most of our work has been on the technical aspect, but I will give a couple of points also on the regulatory and cultural one. For example, we still don't have a metric to assess how efficient is a fan. There are some out there, but they are very limited. They don't focus on why we have them. So they look at, for example, of how much air do they move over how much power. But it's better to look at how much is the cooling effect of fan compared to how much energy is using it. And when we did the test about this index, we found something consistent. If you had a DC fan, this is order of magnitude sometimes more efficient than the others, several times. Why? Because the type of the motor, basically, it's better transforming the electrical energy into mechanical energy. How do you recognize if a fan is DC? Very simple, it tends to cost more. And second, it has different levels, many levels of control, sometimes continuous, sometimes 7, 8, 20. If a fan has only 3 levels, then you're sure that it is an AC fan, so don't buy it. There was very little information about the fluid dynamic inside the space. We have done the most detailed measurement in the world. We basically measure airspeed every 20 centimeters in the entire volume of a room. We took that data and we did it for a single fan. There was some work on it, but also we start to look at the interaction of fan and how the two affect the airflow into the space. We took that database, we publish it online. We also developed a tool for visualizing them. So in case you are good with CFD analysis, you can download that data, calibrate your model, and start to study more, because we know very little about the behavior of fan, in particular when they interact into space. We also work to develop a standard. We worked for almost 10 years with ASHRAE to try to develop a certification program for fans, so we know how much air they are moving. Because if we don't have that information, we cannot design for it. It's a simplified way of measurement, and based on extensive number of tests of different types of fans, small, large, we were able to develop an open source design tool. So you can go there and you give the information about the room, you give information about the size of the fan, where you want to locate, and the fan will give, and the tool will give you an average airspeed in the space, the maximum, the minimum, and a cooling effect. Unfortunately, this is only for ceiling fan. We need also something for desk and standing fans. This is integrated with the comfort standard, the ASHRAE comfort standard, that now is starting to be very different from the ISO standard, mainly because we remove the PPD model and we integrated the PMV and the SCT model in order to better to take into account the effect of airspeed. And I will come back to this point later on. I noticed today that many of you are plotting data for thermal comfort study. If you have a lot of data through simulation or through measurement, and if you're familiar with Python, then you can use this library to process the data. Otherwise, Marcel Schweiker has another nice library in case you use R for that analysis. So we started to go into a space. In this case, it was a lab. We gave people a fan. We did a test with 23 degrees C, and then we went to 26 degrees C, and then we went to 29, and then we did a case with and without fan. We have, I think, roughly 50 to 60 people. And a suggestion, if you're doing an experiment, tend to go to as high number of subjects as possible. It's usually only a small fraction of the cost compared to the cost to pay your salary and all the time that you invest in data analysis and in publishing the work, in particular if you have to pay for the publication. And so try to have many subjects, so your uncertainty is reduced. What we found is that when we gave a fan, 100% of the subjects were satisfied. We were very happy of this result. We went up to 29 degrees, but that was already too warm for some of them, but still better than the 23. Here we were in Singapore. Then we went to a real office in Singapore. This is a private corporation, and they have already ceiling fan. It's a German corporation, so there was a mix between people from Germany and natives from Singapore. And we started 23 degrees, 54% of the people found the space acceptable. When we increase the temperature point and we turn on the fan, acceptability increased. And so we went to around 90%. And in that specific space, the dressing was quite formal. When we went to 27 degrees, we started to see a decay. And there is an interesting study to go on to say, I don't think that in many type of office environment we can easily go to 30 degrees, at least not in the near term, not with substantial adaptation, but we can easily go to 26, 27, maybe 28 degrees C. Another study that we did was about flickering. There is almost nothing about this issue. And flickering happens when there is a fan and the light is behind the fan. Manufacturers suggest that you should never install in that case, but even if you keep the light far from the fan, you can still have, in some point of view, some flickering. And if you have white wall or white floor that are very useful for daylighting, then you may have a lot of flickering. And that is a complex problem because you need many fans in the space. That's another thing that we didn't know at the beginning. We thought that one single fan was sufficient. No, it's like lighting. You cannot design lighting and have only one light in the space. The same is with air movement. We need several of them. So the interaction between them plus fire is very important and understudied. Here was a little study where in a climatic chamber we had a transparent fan and an opaque fan. So this one is the opaque, this is the one that is transparent. And we found that people tend to like a little bit more the transparent one. It's also some small effect on performance. Do fans save energy? Yes, a lot. We have done research, I started almost now 14 years ago, first through simulation in Europe, then we repeat them in the United States, we've done them in Singapore, and in general, as a rule of thumb, you can save between 7 to 15% for every degree that you increase or decrease the temperature set point. Then we went to real buildings. This one is a study that we did in the Central Valley in California, low-income community. I think it was around, I don't remember how many buildings, several buildings, 13 buildings. We installed many fans, around 100 of them. We look at the result for almost 2.5 years. And we did nothing. People did what they wanted. We didn't give advice on please increase the temperature set point. Basically, we gave the fan and say enjoy it. And what we noticed was that, first of all, the fan were not used at very high speed, something around 0.5 meters per second. Temperature was increased of a couple of degrees, not humongously, but we found substantial energy saving. In some situation, 60% energy saving. And then during one of those periods, the chiller faded and people didn't notice basically. Let's go now to the standards. And this one is taken from the Singaporean building code that was active a couple of years ago. When the air conditioner is in operation, the dry bulb temperature should be between 23 and 25 degrees C. Air movement should not exceed 0.3. When I saw that, I thought, are they crazy? And the reason is not completely crazy, it's because if you have an air conditioner and if you dump air on people, people can be uncomfortable. But this solution should not be limiting the air, should be increasing the temperature set point. Similar in Europe, the standard that you use allowed some air movement, say under summer comfort condition with indoor perfect temperature above 25 degrees, you can increase the velocity, but you should increase the velocity under personal control. And I find that this is very unfair. Why? Because we are not saying the same for air temperature. You are allowed to reduce the temperature set point only if it's under personal control. And still, we are finding 40% of the people that are dissatisfied, mainly in air-conditioned buildings. We should treat these two leverage that we have about comfort equally. And when we quantify the effect of air movement, here is a screenshot taken from the table. I hope this is an update one. Let's say that if you have, for example, an airspeed of 0.6, the cooling effect is 1.2. By using the ASHRAE model, same input, we get a cooling effect of 2.8, almost 3 times higher. So the European standards undercount the effect of air movement. And that can play a major role in sizing your system and the amount of money that you can save on the design, in the installation of your chiller, plus the operation, because when you install a big chiller and then the chiller run at low percentage, then not very efficient. We were able to give solid and lasting contribution to the code, both in the United States and in Singapore. Now, this one is from the Green Mark certification in Singapore, where they encourage now the use of air movement instead of discouraging. And you can get some extra point if you use air movement. Let's now jump in the issue of performance. Bjarne before mentioned the work from September and Fisk that was done in 2006, and they came out. They did an analysis based on temperature, not PMV. Then that graph was transformed later on in the ASHRAE Handbook of Fundamental using PMV, but all the studies are based on temperature, and they found that the peak performance were something around 22 degrees C. And as soon as you move and increase the temperature, you have a reduction of around 2.5%. And so that's a big deal. If we believe in this number, that is a killer in a project. We hear our design partners at the Center for the Built Environment come in there and say, Stefano, we would love to install fan, but look, if we go to 77 Fahrenheit, that is 25 degrees C, not very high temperature, we can lose a significant amount of money. And so we were very concerned, and we went back and we tried to access the data. The data were not accessible. So it took us a long time to find someone that wanted to sponsor the research, and we collect all the original data. We put them together. We use 2 independent methods by just looking at the image published, and then by re-looking at those papers and recreating that data from the paper that they use. And what we found was shocking. The accuracy of that model was 5%, meaning that 95% of the variance was unexplained. And most importantly, and this is the most important point, we could fit any model through those data and get similar performance. So it was a decision to find a specific model, in that case a quadratic one, that gave a specific value. So we thought, okay, let's look at more data. And so we started from that database. We look at the more recent literature. We increased the data set. We found roughly 35 studies. We have almost double the number of points, and that we did almost all type of analysis. We look at different type of model, linear model, quadratic model, cubic model. We did a lot of machine learning, different type of support vector machine, and so on and so on. And the result was always the same. Very low prediction accuracy, and the zero model that basically said that there is not a relationship was giving the same accuracy. And so we concluded that by taking this approach, we cannot use that model, and we don't have any equation to be applied in practice for relating the temperature to performance. This does not mean that the thermal environment does not affect performance. It just means that as we have now, if we try to aggregate data together, we don't have a reliable equation that we can apply in practice. We knew that this one was very controversial. It was even controversial between the author of the paper. And so we decided to open source the data. All of you can go there. We develop a tool where you can select the subset of the data, and you can build any model. Do you want a model that the peak performance at 20 degrees? You can build it. Do you want a model that the peak performance is at 24? You can find a combination. Do you want a model that says that there is not an effect between 20 and 28 degrees? You can do that as well. Another work that we have started recently in collaboration with Ollie J is that right now the World Health Organization, the CDC and EPA are putting a limit on the use of fan during heat waves. According to the experiment that Ollie J has done, we can go much higher. And therefore, we thought that it was important to give a tool that people can use to see how much they can use air movement. And here the limit is usually around 35 degrees, because if the air temperature is high than the skin temperature, people are concerned that, in particularly the elderly, may not sweat enough and therefore could be a risk. And so we take all this in account. We made an open source tool where you can put the airspeed, the metabolic rate, and the clothing, and then we give range where we think that fan can be used. And what we found is that in most of type of heat waves, fan can still be beneficial for people. I think that more physical experiment and lab experiment are needed before going to the World Health Organization and change that limits, but I think it is a likely pattern there. Let's end up now with the cultural aspect. I don't want to spend too much time on it because many of you have already touched on that. There's been decades of association with air conditioning, with higher hygiene, higher income status, higher life. But we start to see a change. A change is already happening. We now see high-end consulting firm, very nice office that are designed by using fan. Here's an example of one of the largest DPR, one of the larger construction company in the United States, DPR, where in all their new office, you can see over here, you have a fan installed. In many cases, like in San Francisco, they didn't need to install a chiller, big saving right at the beginning of the project. This is a project I really like. This is a typical office space in the Bay Area, built on spec, only focus on cost. This one was a retrofit, and they were able to achieve a zero energy building. How? Punching hole on the walls, some daylighting, that lighter colors, and over here you can see fan to cool people. We see a lot of projects now. We have WOHA, that is, arguably one of the best architectural firm now in Southeast Asia, started to use fan everywhere, both indoor and outdoor. Here's an award-winning building in Singapore, the Kapung military, where outdoor now they use a lot of this fan to create some movement. You stop the sun, you increase the speed, you can be comfortable outdoor at high temperature and humidity. Here's another spectacular project designed by Transolar in Singapore. This is the National University of Singapore, their new architectural space. If I remember correctly, the architect was here from the UK, and they increased the temperature point to something between 26 to 28, and they have fans and high satisfaction level they found in that buildings. We started to see fans that are not spinning, because usually that one are the most efficient, but not everybody like them. Here you can see a case of a fan encased within a space, so you don't see the blade moving. We also start to see a lot of product coming out. You have the fancy Dyson fan that may also, a little bit clean the air, but they are very expensive. But over here you see other type of fan. This one are some pictures I took in Singapore. This one is $10. I use it in my desk. It uses less than 2 watts. I cannot measure it actually how much power it's using, and it's okay to keep me comfortable at 25 to 26 degrees. If the temperature go higher, then I need to use a little bit bigger fan. Maybe it's using 15 to 20 watts to keep in comfort. Very affordable as well. We are now doing a series of projects. We retrofitted an entire floor of a building, 80 desks, 800 square meters, and we installed a ceiling fan and desk fan. In this case, we use the Dyson fan, but we also give option for lower cost alternative. And now we are going in many buildings in Singapore as a low cost intervention. We go inside and say, you want to save some money, increase the temperature point, we give you some fan, and you will see that you probably increase the occupant satisfaction and reduce the energy consumption. And we are now collecting the data and hoping to report the result. So today I hear a lot of negative feedback about air conditioning. I don't share the same feeling. I think that air conditioning has been a great invention for humanity. It saved a lot of people, it improved the comfort, but it should not be the only solution. And it should not be the first solution. And so this presentation tried to make an argument that we should first move the air, and when fans are not able anymore to provide comfort, then we turn on air conditioning. And of course, this does not exclude all the other very important solutions, like relating to buildings. Thank you very much.
Thank you so much, Stefano. I'm afraid we sort of run out. We run out of time for questions. But Stefano is here, and you can contact him on various on his email and so on. But absolutely brilliant talk. So thank you very much for that, Stefano.